Welcome back to another episode of Introductory Organic Chemistry. Today we're going to talk about chemistry involving enolates. But before we get into that, let's talk through some of the practice problems I assigned last lecture. So in this first problem, we take the starting cinnamaldehyde. A cinnamaldehyde is when you have a benzene ring conjugated to an olefin, which is called a styrene when we have that, followed by an aldehyde right away. So this is a derivatized cinnamaldehyde. So under one set of conditions, we can add an ethyl group into the beta position. However, under other conditions, we can add an ethyl group to the ipso carbon. So in the first set of conditions, we do a conjugate addition, which is a 1,4 addition, using a cuprate, which is what we talked about in last lecture. So first we take diethyl lithium cuprate, that adds to the beta position, and then the alpha position, which is an enolate, is protonated by acid during workup. In the other case, if we want to add to the carbonyl doing a 1,2 addition, we have to use a Grignard reagent. And then subsequently in workup, we protonate the resulting alcohol. In the next problem, we take this acyl chloride and we treat it with either methyl magnesium bromide or this dimethyl lithium cuprate. And because Grignard reagents are very reactive, it will react twice, first with the acyl chloride, then the intermediate ketone, affording this tertiary alcohol product. However, when we treat the same acyl chloride with dimethyl lithium cuprate, because cuprates are soft electrophiles, we'll only get the ketone and it'll stop reacting. And if you're not sure why this is, just recall from the previous example we just went through that cuprates don't like to do 1,2 addition, and if a copper species was to react with a ketone, that would be a 1,2 addition. Now, the reason it reacts with the acyl chloride is because the chloride is a good leaving group, and the cuprate can still help coordinate the chloride and make it easier to eliminate and form lithium chloride. In this final example, we have this primary alkyl iodide, and in one set of conditions, we treat it with a cuprate. In another set of conditions, we treat it just with a lithium species. So this cuprate on the left would actually be derived from N-butyllithium, two equivalents in the presence of a copper salt, such as copper 1 bromide. In the left case, we have an SN2 type reaction. It isn't quite an SN2 reaction as it involves a transition metal. This would be called something called a reductive elimination after an oxidative addition of the alkyl iodide to the copper. That's beyond the scope of what we're currently talking about, however. So for simplicity's sake, you can view it as an SN2-like reaction as it forms an sp3-sp3 bond. And so this would essentially just extend this carbon chain by 4 carbons. However, in the right case, because we just have an alkyl lithium species, all that would occur is the lithiation of this position. Now, if you left this reaction long enough, you might start seeing some sort of elimination process type happening, but you'd likely have to use a weaker base such as LDA to see that happen, or maybe even potassium terpetoxide or DBU. So with that, let's get into today's material. But first I want to introduce some additional functional groups. So there's these reagents that are really useful for trapping enolates. And so sometimes when we generate an enolate, we want to isolate it so that we can do subsequent chemistry in a really clean way. I'll show you an example of what I mean later. So 3 different traps that you can use for enolates. These aren't an exhaustive list of traps, but these are members of 3 different classes. Include triflating agents such as phenyltriflamide, silating agents such as TMS chloride, as well as dicyclohexyl boron chloride, which is a borlating agent. These electrophiles are all hard electrophiles. So if you recall from last lecture, we were talking about copper being a soft nucleophile versus magnesium being a harder nucleophile for Grignards versus cuprates. Now these are hard electrophiles. So if we have an oxygen present, an O-, these would prefer to react at oxygen over something like carbon. So if we form an enolate, these should react at oxygen. Now what I mean is specifically like this. If we deprotonate the alpha position of a ketone, which you can do with a weaker or a stronger base, you'll deprotonate it, forming this enolate. This enolate can then be trapped at oxygen if we use a hard electrophile, such as the 3 reagents we just discussed. So these would form, in this case, a boron-oxygen bond, in this case, a silicon-oxygen bond, or in this case, a sulfur-oxygen bond. However, if we use a soft electrophile, something like an alkylating agent like iodomethane or benzyl bromide, we'll actually see reactivity at the alpha position, at the carbon. When we want to generate an enolate, we can start with a ketone or an aldehyde. We can even start with something like an ester or an amide, but it's more common to see aldehydes or ketones used. We treat it with a strong base. It has to be strong enough to deprotonate the alpha position. Once we form this lithium enolate, which in the case of LDA is usually the Z enolate, the bulkier the base, the more we favor the Z over the E enolate. we can either do chemistry at this stage, or we can do chemistry after trapping the enolate with some sort of trap, such as the hard traps that we just talked about. Now, one of the reasons why we use LDA is it's a really strong base and it remains soluble in THF at -78. Previously, people used to use bases such as sodium amide, but the problem with sodium amide was it wasn't very soluble, and it could lead to disproportionation reactions for aldol type chemistry, where you'd start deprotonating the product and it would get really messy. So LDA remains the base of choice even in contemporary chemistry for the most part. So why should you care about enolates? So the main reason you would want to care about enolates is you can form carbon-carbon bonds. And as illustrated with the Grignard reaction, with Gilman reagents, with organolithium reagents, carbon-carbon bond forming reactions are among the most important reactions in organic chemistry. So in this case, you can see that this enolate reacts with an alkylating agent to form a new sp3-sp3 carbon bond. So this is like a very useful way to create bonds in organic chemistry. One of the things we can do to generate a Z versus an E enolate, in this case we have a TMS enolate. Sometimes silyl enolates are called silyl enol ethers. When we use a less bulky base like lithium diisopropyl or diethyl amide, we'll actually prefer to get the E enol. However, if we use a bulkier base such as lithium TMP, we tend to favor the Z enolate. Now, in the previous example here, where I said LDA favors, for the most part, the Z enolate as the major product, you don't favor it that much. So if you want a really good ratio of Z to E, you'll use a bulkier base like lithium TMP for the most part. Now, if we only have like a CH3 versus a multiple substituted position, we'll get better selectivity. But for something like this, where we're going for a secondary position versus a tertiary position, there's not too much selectivity, so you have to really get picky about your choice of base. So for the most part, when you're using these lithium bases, you're going to get the kinetic enolate, especially if you're using super stoichiometric amounts of the lithium base like LDA. If you're using like 1.1 or 1.2 equivalents, you know, if there's traces of water, that'll get deprotonated, but then all of the ketone will get converted to an enolate, and then there can't be any equilibrium. However, if you want to get the thermodynamic enolate, which is essentially just the more substituted olefin, you can use different conditions. So you can use triethylamine in refluxing DMF for 48 hours, and you'll tend to get the major product, which is the thermodynamic enolate. You could also do this clever trick where instead of using a super stoichiometric amount of LDA, like 1.1 equivalents to get the kinetic enolate, you use something like 0.9 or 0.8 equivalents, and you just let it sit for a really long time, and then slowly it'll disproportionate to the thermodynamic enolate. But typically, if you want to leave a reaction at -78 for like a really long time, there isn't a convenient way to do that for most labs because you have to keep replacing the dry ice in the reaction. So for the most part, this is the method that you'll see used. Now you might be wondering, why would we want to trap this? Why wouldn't we just do chemistry with the enolate itself? Why do we have to trap it as the TMS-Enol ether? And I'll show you exactly why. So here in this first example, we're doing kinetic lithiation of an ethyl versus a propyl group. Now selectivity-wise, this would be pretty hard to achieve because, you know, they're both similarly sterically encumbered, but you would get some slight difference in distributions. You should probably favor blue slightly. So we lithiate and then alkylate with an alkylating agent. Now you can see we get a mixture. These will be really hard to separate because they're almost the identical molecule. They're not quite identical, but they're pretty close. Now, if you were to trap this as a TMS-Enol ether, you could separate this one from the other one, hopefully fairly easily. Once you've isolated this, though, if you alkylate after activating with something like methyl lithium to regenerate the lithium enolate, you'll get one single product. So if you make the enol ether, you can get a single product via functionalization. Now, some cool chemistry you can do with lithium or with TMS-Enol ethers includes the treatment with methyl lithium to unmask the lithium enolate, like I was just saying. The methyl group just attacks at the TMS, forming tetramethylsilane as a byproduct when the lithium enolate is generated. However, if you treat a TMS-Enol ether in the presence of a Lewis acid, such as titanium tetrachloride, and a good SN1 electrophile like this tertiary chloride, we'll get a carbocation that can be attacked by the electron density of the enol ether, and then the TMS group can be unmasked by attack of the chloride, reaffording the ketone as the final product. And these reactions work really well, especially with tertiary chlorides, allylic chlorides, propargylic chlorides, and benzylic chlorides, and bromides, etc. Now, one really cool trick that you can do with this chemistry is you could add in a cuprate. So you remember the Gilman reagents do 1,4 addition. You'll form a lithium enolate. Now, I draw this as a lithium enolate, but because there's copper present, this is actually kind of a copper enolate as well. There's like, different cations moving around. And it's just known that these copper enolates aren't very reactive. So you could say that you want to quench with an electrophile and maybe it would work at this stage, but you'd still be better off to just add in TMS chloride anyway. Part of the reason for this is this TMS can also complex this ketone a little bit, which makes this carbon double bond carbon more electrophilic, which makes it easier for the cuprate to attack. So TMS accelerates this reaction. Additionally, you might be worried that because these are nucleophiles, it might react with the TMS chloride and you might form an R-TMS. But because cuprates are soft electrophiles and TMS chloride is a hard electrophile, you won't get a soft nucleophile coupling with a hard electrophile that easily. So these will tolerate each other, so you can have both of these in the same pot. So once the 1,4 addition does occur, you can trap the enolate as a TMS-Enol ether. You can do column chromatography, isolate it, and because of the mechanism of this reaction, you'll only get one TMS-Enol ether. You won't have any of the double bond on the opposite side of the ring. So you can do really good regioselective chemistry with this. So if we purify this, put it in another reaction, treat it with methyl lithium, the methyl group attacks at the TMS, forming tetramethylsilane as a byproduct. That lithium enolate can then be trapped with an electrophile, such as N-bromosuccinimide, or an alkylating agent, such as benzyl bromide, etc. So this is a really useful trick to convert a pretty boring starting material into a doubly functionalized product, which also has additional positions for functionalization if we want. Now for this lecture, I'm going to assign two practice problems. First, starting with this ketone, propose conditions that would afford you with the product on the left and the product on the right. Multiple steps may be required. In this other example, I'd like you to show which base or which lithium enolate would form under the given reaction conditions. And I want you to determine whether it's the kinetic or the thermodynamic enolate. And with that, I hope this has been a useful lecture. If you have any questions or comments, please leave them below. If you have any opinions or comments on how you think this series could be done better, I'd be happy to hear them. And I hope you have a great day. Thank you.